Hi guys, this is lecture 31 today, or sorry, before we get into that, I know a lot of you are feeling some anxiety about the exam. I should have information for you by the end of today about when the exam will be, how much time it'll take, and the format, etc. Okay, I'm sorry that it's been so slow getting back to you, but we're trying to coordinate between all the classes of 105 to make sure everyone's getting a similar experience. Okay, today we will be talking about percent compositions, empirical formulas, molecular formulas, and combustion analysis. So we're going to start out this conversation by looking at chocolate. And I know what you're thinking, should have stocked up on chocolate. But what I have shown here is white chocolate, brown chocolate, and dark chocolate, or by brown chocolate, I mean milk chocolate. But what is the difference between all of these guys? Well, for it to be considered dark chocolate, it has to have more than 50% cocoa. And I know that's probably pronounced cacao, but I never remember when to say cacao and cocoa, so we're just going to call everything cocoa. For it to be milk chocolate, you usually have around 10% cocoa, but it can be higher or lower. And then for white chocolate, that's actually just made of sugar, cocoa butter, and milk, and it doesn't have any cocoa powder. So what is the big difference between all of these guys? It's their percent composition, the amount of cocoa that's involved in making each of them. So here I just have some Lindt chocolate bars, and if you're wondering when it says 90% cocoa, that means 90% of the chocolate, or the mass of your chocolate bar, actually consists of cocoa beans, ground up cocoa beans. Well, we're not talking about chocolate too much, we're talking about molecules here. So in molecules, we try and measure something called our percent composition. In molecules, in mixtures, in different samples. And percent composition is the percent by mass of each element present in a compound or mixture. So this is how we calculate it. If we're looking for the percent composition of a specific element, we're going to take the mass of that element, divide it by the total mass of our compound. And we're going to multiply it by 100%. That'll give us the percent composition of that element. So more specifically, to calculate the percent composition, we're going to assume we have 1 mole of a compound. That'll just make our calculations simpler. Then we'll calculate the molar mass of the compound. We'll calculate the mass of each element present. And then we'll divide the mass of each element present by the total mass of the compound and multiply each of those by 100% to get the percent by mass of each element. As a practice or example, let me show you some rusty nails. I guess those are screws. I guess they might be bolts. I don't know. I'm not a construction worker. My dad is, but that's another story. So first, let's assume we have 1 mole of rust. So we've scraped a bunch of rust into a container. Now let's calculate our molar mass of the rust. So this is going to be 2 times the molecular weight, or the atomic weight of iron, because there's 2 irons in this molecule, plus 3 times the atomic weight of oxygen. And that is going to give us 159.69 grams of iron 2O3. Next thing we do is calculate the mass of the iron present. So for this part, we're just going to take the first half of this equation, 2 times the atomic weight of iron, and that'll give us a value of 111.69 grams of iron in 1 mole of iron 2O3. The last thing we have to do is multiply this 111.69 by 159.69, and then multiply by 100 to find that we have 69.94% iron. And that is iron's percent composition. Now, since there's only iron and oxygen in this, you can find oxygen's percent composition now by taking 100% and subtracting 69.94. So it has a percent composition of about 30.06%. Let's practice this with our propane molecule here. and calculate the percent by mass of carbon in propane. So what we need to do here first is calculate our mass of propane. So there are 3 carbons, 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we'll do 3 times the atomic weight of carbon plus 8 times the atomic weight of hydrogen, and we'll get out 44.096 grams. And that is our total molecular weight of propane. Now let's figure out how much of that is carbon. We're going to figure out the mass of the carbon by taking 3, the number of carbon atoms, multiplying it by the atomic weight of carbon, and that'll give us a value of 36 grams. And of course, we take the 36, divide by 44 times 100%. We find that there is 81.715%. If I look over here at the answers, the closest one to that is our 82% right here. And so this is one type of question I could give you. Another one could look like this. I'll make a point real fast here that if you want to practice these iCLICKER quizzes before I go over them, you can always pause the video before I give you the explanation. So in this question, they ask which of the following compounds has the highest percentage of carbon by mass? We have CH4, we have C2H6, C3H8, CO2, and CO. So what we're going to do for each of these is calculate the mass of our entire molecule, and then calculate the mass of carbon. We're going to divide those. So in CH4, the mass of carbon is just 12 because there's 1 carbon, or it's approximately 12. I'm simplifying these numbers slightly. The molecular weight here is 16 because it's carbon, which weighs 12, plus 4 hydrogens that each weigh 1. 12 divided by 16 is 3/4. In this next one, we have 2 carbons, so the amount of carbon there is going to be 24 grams, and 24 plus 6 would give us 30. So we have 24 over 30, which is equal to 4/5. In C3H8, our carbons, since there's 3 of them times 12, that's going to weigh 36. And then 36 plus our 8 hydrogens is going to weigh 44. So we get 9/11ths there. For CO2, carbon weighs 12, oxygen, each oxygen weighs 16, so you're going to have to add those up to get 32. 12 plus 32 is equal to 44. So this is 12/44, and that's less than half, right? And then for CO, this is 12 plus 16, which is 28, so 12/28 is less than half as well. So the species in here that has the highest percent of carbon by mass is going to be our C3H8. Now, you might look at this problem and assume that this is the right answer because it has the most carbon atoms of any of these. You'll notice this has 1, this has 2, and each of these only have 1. Don't assume that the species that has the most carbon atoms is going to weigh the most or have the highest percentage of carbon by mass. There are a lot of examples where that's not true. So always do it the way I told you. Calculate the mass of the carbon, divide it by the total mass of the molecule, figure out which one is the greatest. Don't just assume whichever one has the most carbons is going to be it. Now let's go on to finding percent composition in real life. So how do we do this in real life? Well, it's a little tricky, but for hydrocarbons and other compounds that burn, we just burn them. So this doesn't work for everything. It doesn't work for metals, but for most hydrocarbons, so for most of our organic molecules, most things that we eat, you can just burn them and figure out their composition that way. So when you burn these things, you're combusting them, reacting them with fuel and oxygen, and that's going to give you CO2 and water out as products. And then we can look at the ratios of carbon, hydrogen, and oxygen in our products to figure out the percent composition. So specifically what that looks like is we have a chamber in here with our sample. We burn that with oxygen flowing through. As it burns, it's going to release CO2 and water, and that is going to flow with the oxygen into these traps. We have one trap that absorbs water, one that absorbs CO2, and most everything else flies by. So what we do is we weigh this guy before we start the experiment. We start the experiment, collect all the water, and then we weigh it again and see how much it changed. And that changes in mass will all be due to water being absorbed. And the CO2, of course, gets trapped in the CO2 absorber. And a similar process happens there. And then from that, we can figure out our percent hydrogen. That's what's going to come in our H2O absorber. We can figure out our percent carbon by what's trapped in our CO2 absorber. And whatever's left over, percent composition-wise, is going to be oxygen. Why can't we get the percent composition directly through combustion for oxygen? The answer is because we're pumping tons of oxygen in. So while our sample combusting might be producing oxygen in the form of water or in the form of O2 or CO2, it's going to be mingled in with tons of other oxygen being mixed in here. So we can't tell which oxygen is from the fuel and which oxygen is from our sample. If we wanted to know some other things, such as whether or not there's any nitrogen or sulfur present, we can also have collectors that collect NO2 or SO2 and other absorbers to find different percent compositions. Okay, so let's go ahead and practice this. Let's say we have 0.236 grams of aspirin and we burn that in oxygen. And we produce 0.519 grams of CO2 or carbon dioxide and 0.0945 grams of water. And if we know that aspirin consists only of carbon, hydrogen, and oxygen, and I'll just say that we learned that from other chemical tests, what is our percent composition? Well, let's start with our percent carbon. So we're going to get our percent carbon, from the mass of CO2 that's present. So what we're going to have to do there, though, is take our mass of CO2. So we generated 0.519 grams of CO2. We're going to have to figure out how many grams of carbon that corresponds to. So the first thing we're going to do is take that 0.519 grams, divide it by the molecular weight of CO2 to turn it into moles of CO2. Then we're going to multiply by the mole ratio between carbon and CO2. And that is going to be a 1-to-1 ratio because there is one carbon atom for every molecule of CO2. So we'll multiply by 1 mole of carbon for every 1 mole of CO2. And then we want to figure out how many grams we have. So we'll multiply by the molecular weight of carbon. So here we went from grams of CO2, moles of CO2, moles of carbon, grams of carbon. So our answer is 0.142 grams of carbon. Now to figure out our percent composition, we know we had 0.142 grams of carbon, and we started with 0.236 grams of aspirin. So we're going to divide this 0.142 by 0.236, multiply by 100%. We find that there's 60% carbon. And then we'll do the same thing with hydrogen, except that is not being turned into CO2, it's being converted to H2O. So for this one, we'll divide our 0.0945 grams of water we generated by the molecular weight of water. So now we're in moles of water, but now we need to convert to moles of hydrogen. In this one, we have a mole ratio of 2-to-1 because there are 2 atoms of hydrogen for every molecule of water. And that gets us into moles of hydrogen, multiplied by the molecular weight of hydrogen, then we find that there are 0.0106 grams of hydrogen present. And of course, we divide that by our total mass of our aspirin, times it by 100%, to find that percent-wise, there is 4.48% hydrogen. Now, the last thing to calculate is our percent oxygen. And this is just the remainder. So what we're going to do is take 100%, subtract the 60% from carbon plus the 4.48% from hydrogen, and we're going to find that there is 35.5% oxygen by mass. Okay, so to review all of those steps, when we're finding our percent composition from combustion analysis, we're going to find the mass of carbon from CO2, we're going to find the mass of hydrogen from H2O, we're going to divide each of the masses by the original compound combusted, multiply by 100% to get the percent of carbon and hydrogen. And then we're going to take 100%, subtract percent carbon, percent hydrogen to get our percent oxygen. Now, how do we go, though, from that percent composition to a chemical formula? How do we take this information and turn it into something that chemists can look at and determine chemical properties? Well, we're going to have to figure out our mole ratio. So to do that, we're going to change these percentages into grams. And so we're going to just change this 60% carbon to 60 grams of carbon. Now, we're not actually saying anywhere that there are 60 grams of carbon present. At this point, this 60 grams is a theoretical number. It's just helpful for our calculations. So all we're saying is instead of being 60% carbon, let's say change the 60% to 60 grams of carbon. Then we'll have 4.48 grams of hydrogen, 35.5 grams of oxygen. Then what we need to do is convert these grams to moles. So we're just going to be dividing by our molecular weights. So we'll take this 60 grams of carbon, divide by the molecular weight of carbon, which is 12.011 grams, and that gives us 5 moles of carbon. We're then going to do the same with the hydrogen. Take that 4.48 grams of hydrogen, divide by the atomic weight of hydrogen to find 4.44 moles of hydrogen. And the last thing we're going to do is that with the oxygen. We're going to take the 35.5 grams of oxygen, divide it by the atomic weight of oxygen to find 2.22 moles of oxygen. Now, looking at these, we need these all to be whole numbers to get them into our chemical formula up here. So we're going to have to do some multiplication and division to get these to do be whole numbers. You might be tempted at first to just try multiplying these by different numbers to see what'll get you whole numbers, but that's actually not the right way to go. The first thing you want to do is actually divide all of these by the smallest number. So in this case, our smallest number of moles is 2.22. So we're going to divide all of these by 2.22. Now we find a 1 for the oxygen, a 2 for the hydrogen, and a 2.25 for the carbon. The next thing we want to do now is we still have a ratio here, or a fraction. We need to multiply this, if there's any fractions, by some whole number to make all of these whole numbers. So 2.25, to make that a whole number, we're going to have to multiply it by 4. So we're going to multiply all of these by 4 and get values of 9, 8, and 4. So what this means now is that in our formula up here, we're going to have 9 carbons, 8 hydrogens, 4 oxygens. And we get a structure that looks like this. This is acetylsalicylic acid, which is the formal name of the drug known as aspirin. We can check this guy. It has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. It has 1, 2, 3, 4 oxygens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, just like we predicted from our combustion reaction. So that is how you get to a formula from combustion. But I'll point out that the formula you get is not actually the molecular formula. This formula we got from our combustion reaction is known as our empirical formula. So in that last case for aspirin, the empirical formula turned out to be the molecular formula, but that's not always going to be the case. And actually in most molecules, it's not going to be the case. So the empirical formula is the lowest whole number ratio of elements, which is not always the molecular formula. To give you an example, here is benzene. You've seen this guy a lot by now. And its molecular formula is C6H6, but its empirical formula is CH. Why is that? Well, because in the molecular formula, carbon and hydrogen exist at a 1-to-1 ratio. And so in the molecular formula, your formula you get would just be CH. And so if you do combustion analysis, this CH is the formula you'll get, which is actually the empirical formula for a number of species. Right? So to find the empirical formula from the percent composition, that's not super difficult. All you're going to do is change each percent to grams. So this is what we just practiced. Change each percent to grams. Assume you have about 100 grams of the compound, or exactly 100 grams. Convert all the grams to moles. Divide all of them by the smallest number of moles. Get the mole ratios. And if there's any fractions, multiply them all by a factor to make them all whole numbers. Let me give you a practice problem here. Here I'm showing combustion analysis. In this problem, we have combustion analysis indicating that nicotine consists of 74% carbon, 8.65% hydrogen, and 17.35% nitrogen by mass. What is the empirical formula of nicotine? So if you want to pause the video now and try and solve that yourself, go ahead. Now I will go through it. First step, right? Pretend we have these percents in grams. So 74 grams of carbon, 8.65 grams of hydrogen, 17.35 grams of nitrogen. We're going to divide each of these by their molecular weights to turn them into moles. All right, so that's steps 1 and 2 right there. Now that we have them in moles, you'll notice that these are all weird wonky numbers. So we're going to divide by the smallest number, that is step 3. So we're going to get 1 mole of nitrogen, 6.92 moles of hydrogen, 4.97 moles of carbon. Now in this problem, I will point something out, that this 4.97 and 6.92 aren't exactly whole numbers, but they're fairly close. And they're actually close enough that we're going to assume that they are whole numbers and that there is just some slight measurement error. So when can you do that with combustion analysis? You can do that when you're in your third step, if your moles here are within 0.1 or less than 0.1 of a whole number. So this guy is 0.08 away from a whole number. This is 0.03 away from a whole number. So you can round them up. If it's any more than 0.1, you want to be careful. Just try and convert them into whole numbers. My apologies, I'm getting text messages. But from this problem, you can see that the right answer is going to have 1 nitrogen. So it's not going to be any of these guys. It's going to have 7 hydrogens and 5 carbons. So our correct answer is going to be A up here. Now C, you should be able to look at immediately and say that it's wrong. Why? Because these subscripts right here are not whole numbers. And so we're just going to know immediately that that is not a good chemical formula. Okay, we've made this point that empirical formulas are not molecular formulas, right? But molecular formulas are always a whole number multiple of the empirical formula, which means that you can always take this empirical formula, multiply it by some number, some whole number to get the molecular formula. So in this case, we'd multiply benzene's empirical formula by 6 to get its molecular formula. But how do we know what number to multiply our empirical formula by? This actually gets us into what I do in my lab. which is called mass spectrometry. In mass spectrometry, we actually separate compounds by their mass. The way we do this is by running them through a mass spectrometer. So this is a diagram of a really old version of a mass spectrometer. Mine actually look nothing like this, but this will explain how we do this. So the first thing we do, so we have our sample come through, and it goes through this electron source, which actually rips electrons off of the molecules. And that process then makes all of our molecules positively charged, and it's a little harsh, so sometimes it makes them fall apart. But then once our ions are created, once we've ripped electrons off our molecules, we send them down this path. And I actually really hate this part of the drawing because it looks like we're sending our ions through some sort of metal disc or something. This should be a hole. We just send them through a hole. So these ions, they travel down this hole until they get into a magnetic field. And something you'll learn more about in physics is that when a charged particle passes through a magnetic field, it bends its trajectory, so it curves. And so lighter ions, since they are lighter, it's easier for that magnetic field to turn them farther. And so your light ions turn farther and hit a spot over here, whereas your heavy ions will turn less and hit a spot on your detector over here. So you can spread these guys out. So if we send benzene through our mass spectrometer like this, we will get a spectrum that looks like this. Now often people get confused when they first see a mass spectrum because they say, well, is this your benzene? Well, what are all these other peaks? Well, a mass spectrum is actually a measurement of a few million molecules of benzene. So most of the benzene still show up at this spot right here. What I have on this, our x-axis is the mass to charge ratio of our ions. In this case, you can just think of it as your mass. And on the y-axis is just the relative intensity or abundance of these guys. And so this big peak right here is what we call the molecular ion peak. That means it corresponds to the intact molecule. But like I said, when we're ripping electrons off of our species down here in our electron source, that's harsh, and it causes a certain amount of our benzene molecules to break apart. So that's what these other peaks here are from, is our benzene getting basically ripped to shreds. But from our mass spectrum, we can see that benzene weighs 78 atomic mass units. Everything out here, like I said, is fragments. What we're going to do is take this molecular ion mass, 78 atomic mass units, and compare that to our empirical formula mass. So to give you an example of how that works, again, here is the mass spectrum of benzene. If you'll notice on the x-axis, we have this big peak showing up at 78 AMU. Our empirical formula was just CH. We're going to calculate the weight of our empirical formula, and that would just be 1 carbon plus 1 hydrogen. So we would get a weight of 13.0 grams per mole, or in other words, 13.02 AMU. Remember that we can switch back and forth between these atomic mass units and grams per mole. We know that our molecular formula is just some whole number multiple of our empirical formula. So what we need to find is the number that we'd multiply 13 by to turn it into 78. The best way to do that is to take 78 and divide it by 13. So 78 divided by 13.02 actually gives us a value of 5.99, but that's close enough that we know it is 6. So then what we're going to do is take our empirical formula of C1H1, multiply it by 6 to get C6H6. Now you might be wondering, how do I know that this is close enough to 6 to round to 6? Well, in this calculation, when you're dividing your molecular weight by your empirical weight, it should always be a whole number. And so you can pretty much always assume that it's going to round to a whole number.
If you get something that's like 5.5, then you probably just did something terribly wrong. You should check your work. All right, now, how do we find our molecular formula from our empirical formula? The way we're going to have to do it is we're going to calculate the mass of the empirical formula. These are the steps I just did. Divide the molecular ion mass by the empirical formula mass. And this should get you really close to a whole number. And then we're going to multiply the subscripts of the empirical formula by the factor that we calculated in step 2 to get the molecular formula. Okay? Let's practice that. Here we found the empirical formula of nicotine to be C5H7N. So we just did that with a combustion reaction. And our mass spectrometry analysis shows the molecular weight of nicotine to be 162 grams per mole. So that means our molecular ion peak showed up at 162 on our x-axis here. What is the molecular formula of nicotine? All right, if you want to pause it now and work this problem by yourself and then check with my solution, you can. So go ahead and pause it. Okay. First, we're going to have to calculate the mass of our empirical formula. So C5H7N weighs 81.1 grams per mole. If we divide 162, which is the mass we found from our mass spectrometry, then we get 162 divided by 81.1. That gives us a ratio of 2. So we're going to have to take our empirical formula, multiply it by 2, get C10H14N2. That's right there. So this is the structure of nicotine, the highly addictive substance found in cigarettes. It's kind of a cool structure, though. I mean, it kills people, but it's a cool structure. All right. So we've gone through a lot of lists of steps. So let's summarize them all in one big long list of steps. Okay. If we want to find the molecular formula from the percent composition, how do we do that? Well, first thing we do is change everything into a percent, or change each percent to grams, convert the grams to moles, divide all of those moles by the smallest number of moles to get our mole ratios. If there's any fractions, multiply them all by a factor to make whole numbers. This will give you your empirical formula. Once you have your empirical formula, you're going to have to calculate the mass of the empirical formula. Divide the molecular ion mass by your empirical formula mass, and multiply the subscripts in the empirical formula by that factor. So we're going to have a practice problem on the next page. So if you want to pause this and write these steps down, or just take a screenshot of this or a picture with your phone, that will be helpful for the problem on the next slide. Okay. Here is our problem. Vanillin is the compound containing CH and O that gives vanilla beans their characteristic flavor. Combustion of 30.4 grams of vanillin produces 70.4 grams of CO2 and 14.4 grams of water. The molecular ion of vanillin in the mass spectrum given above, right here, is 152. So this is its highest peak. So that is its molecular weight. Now, what are the percent composition and the molecular formula of vanillin? If you'd like to pause this video now so that you can work this problem, go ahead. Okay, the first thing we're going to have to do is figure out how many grams of carbon correspond to this 70.4 grams of CO2. So we'll take that 70.4 grams, divide it by the molecular weight of CO2, multiply by the mole ratio of carbon to CO2, which is again 1:1, multiply by the molecular weight of carbon. Now we know there were 19.21 grams of carbon produced or released when we burned 30.4 grams of vanilla. So let's turn that into a percent composition. We will divide by 30.4 grams of vanillin and multiply by 100% to get 63.19% carbon. Next, we got to figure out how much hydrogen, or the percent composition of the hydrogen. So we'll take the mass of water we got from combustion,
divide by the molecular weight of the water, multiply by the mole ratio between hydrogen and water. So that will give us a value of 2. And then we will multiply by the atomic weight of hydrogen to find that we got 1.61 grams of hydrogen. We'll divide that by the total grams of vanillin, multiply by 100% to find that we got 5.30% hydrogen in this compound. Now we know how much carbon and hydrogen, and the question says that it just has carbon, hydrogen, and oxygen. So we'll figure out how much oxygen is present by taking 100% and subtracting this 63.19% of carbon plus the 5.30% hydrogen. Just got to slow down while I'm talking. And that'll give us 31.51% oxygen. Okay, now we know the percent composition of our vanillin. Now we got to turn this into an empirical formula and then into a molecular formula. So let's pretend now that instead of percents here, we have grams. So we're going to have 63.19 grams of carbon divided by the atomic weight of carbon. Now we'll say we have 5.26 moles of carbon. Now again, just a reminder, everything right here is just theoretical. We don't actually have 63.19 grams of carbon, right? We're just saying that we're going to pretend this 63.19% carbon is 63.19 grams of carbon. And that is just to simplify the calculations here. We're going to do the same with hydrogen, turn that into moles, and the same with oxygen. So we have equal numbers of moles of carbon and hydrogen, and our moles of oxygen are a lot less. So now we need to go from moles here to a mole ratio by dividing by this 1.97 value here. And that will give us 2.67 moles of carbon, 2.67 moles of hydrogen, and 1 mole of oxygen. This 1 mole of oxygen is promising. These guys indicate that we're going to have to multiply by some number. Now, if you didn't realize this already, 2.67 is actually equal to 2 2/3. So we're going to need to multiply these all by 3. Now, how did I know that? Just because I happen to be good with fractions. If you're not good with fractions, you can always just try multiplying by a bunch of different small numbers. So if you start with 2, then 3, then 4, and 5, until your mole ratio here all turns into whole numbers, that's a perfectly fine way of doing it too. It's usually not going to take too many tries. You're usually not going to be multiplying by more than 4 or 5. I might throw in a random question where you have to multiply by 7 right. So, but anyways, if we multiply all of these by 3, we find that there's 8 carbons, 8 hydrogens, 3 oxygens. So that would be our empirical formula, C8H8O3. We calculate the mass of our empirical formula. We find that it weighs 152.15 grams per mole. We compare that to our molecular formula we got from mass spectrometry of 152. We do 152 divided by 152.15. That is about 1. And so we're going to take our empirical formula, multiply it by 1, and get our molecular formula of C8H8O3. And that is how we get our molecular formula of vanillin. Now, just for fun, here is the actual structure of vanillin. And I just wanted to show you this other guy called orthovanillin. So vanillin and orthovanillin are very similar, except in vanillin, it has this OH group pointing down over here, but in orthovanillin, it's actually over here. So the way this works is if something is here, it's ortho, if it's here, it's para, or it's meta, and down here, it's para. So this is actually paravanillin. You don't actually have to know ortho, meta, and para at this point. You will when you get into OChem, but for now you don't have to worry about it. But here is the mass spectrum for vanillin, and here is the mass spectrum for orthovanillin. You'll notice they both have a big peak over here at 152, The highest peak for orthovanillin is actually at 151, so it really likes to lose one hydrogen. So moving this OH group from here to here actually makes it real easy for that hydrogen to fly off when you rip off its electrons. But beyond that, you can see that these mass spectra are not exactly the same. They're similar, but in vanillin, you get this big fragment, or this fragmentation peak at 136, whereas in the orthovanillin, there's a peak at 137, maybe a small peak at 136, but they look different. The same at 122 and 123, they look different. These guys look different. So even though these guys look very similar, they're different enough that we can always tell vanillin from orthovanillin. And these mass spectrum are really, or these mass spectra are really reproducible. So it's actually not hard to differentiate these two. So vanillin actually tastes good. Orthovanillin will give you a stomach ache. It also irritates skin and eyes. So you don't want to eat this. Vanillin's good. But then if you change vanillin slightly, give it an extra CH2 right here, change it to ethyl vanillin, it actually has a similar taste but vanillin, but it's 3 times stronger. So this is a fun little substitute. Anyways, that is it for percent composition, combustion analysis, empirical formulas, and molecular formulas. As always, if you have questions or concerns, feel free to reach out to me or the TAs. I will try and have them post video reviews of some kind or host video chats to review for the exam that is coming up, and I will have more information for you on the exam by the end of today. All right, thanks. Have a good one.